Assalamualaikum warahmatullahi wabarakatuh. My name is Eri Hernando, and in this video, I am going to do a presentation for my Electronic Instrumentation Design final project, where we need to explain and research, made a summary about a paper related to DC or AC bridges. Alright, so for this final project, the paper that I found is this. The title is a 4-terminal coaxial-pair Maxwell Wein bridge for the measurement of self-inductance. So here is the author. His name is Marcel Cote. I believe he's Canadian. He's from Canada, and that's why the research is also conducted, I believe, with his organization, the National Research Council of Canada. And yeah, this is a little bit of his background too. Okay, next we get into the intro. Okay, so the paper said that in the introduction, this is the basic Maxwell-Wien bridge, where they mention, and I quote, that they are no longer in serviceable condition. So that's why they propose a new and improved bridge. They developed the 4-terminal coaxial-pair Maxwell-Wien bridge. Okay, I think we can go to the next part, which is the circuit. So, with the 4-terminal design, it has an advantage that the main impedance of the bridge can be independently characterized. Also, corrections due to the interconnecting cables are separately evaluated and significantly smaller and better. Okay, here we have the bigger picture of the bridge. We have source, we have the Wagner connection, the main adjust, we have the capacitors, resistors, and then the Kelvin balances, as well as the current dividers. So we have here the left-hand Kelvin balance, also known as the De Sautis bridge. For the right one is also another Maxwell-Wien bridge. So the Kelvin is used to minimize the effect of low current cable impedance on the measurement to achieve the source and main balances that are iterated until simultaneous zero potentials are achieved at the Kelvin combined network's outputs. Okay, so yeah, the impedance of the resistors pose a problem due to their small but finite time constants and unknown frequency dependencies. So yeah, this is the bridge equation that they gave, and can be written as this, where ZR1 and ZR2 and ZR in J are the complex impedance of the respective resistors, as well and the ZC and ZC in, also the impedance of the capacitors. We have alpha and beta as the main balance of IVD dial settings, and here we get the ZL equals to J omega Lx per Rx, where the Lx and Rx can be seen here. Okay. Of course, when they do the bridge, they have the resistor component as well as the others. The resistors that they choose is the Fichet type S102. So no, but this image is not this specific model. But yeah, for the resistors, they use I believe the 10k ohm values, but they then in the paper they also mention to configure it a different way using different ratios, etc., etc. So for the resistors, they do a frequency dependence test. For the next capacitor capacitor, they use the general radio model GR1482. They did a temperature dependence for the DC resistance of the capacitor. Okay, the next part is the inductor. They did a temperature dependence test as well for the inductor. And yeah, okay. Next is the test result. In this graph, we have the result of the frequency dependence of the test that they did to the resistors. And then here we have, so the resistance versus temperature data are fitted to a second order polynomial of the form. So yeah, this is the formula. And the next one is the resistance versus temperature for the 100 millihenry inductor. Here are the other results. We have four tables. This is the DC temperature coefficient, the This is the for the inductors as well as the inductance for the inductor. So yeah, uh, oh sorry, the Maxwell bridge is used to measure the impedance and inductors at various temperatures at the 1 kilohertz frequency. The table 2 provides the measured temperature coefficient of the inductance with respects to temperatures and DC resistance. With the and the four inductors shown here were compared to appropriate combination of the resistors and capacitors for the bridge. The DC resistance of the inductor was measured before and after the measurement. And our final table here presents the major elements of the uncertainty budget for the 100 millihenry inductor. The uncertainties given for the R1 and R2 in table 4 also includes the frequency, time, temperature, and multimeter linearity uncertainties. Okay, I think that's all for my presentation of this paper. I do believe that I still need to do more research, but because of the time constraint and the deadlines, this is so far the best that I can. Once again, thank you very much for watching. Wassalamualaikum warahmatullahi wabarakatuh.